Welcome to This Explainer. Today, we're diving into a really fascinating topic, finding the unknown, moving all the way from simple puzzles to actual algebra. Now, look, if you're someone who usually breaks into a cold sweat when you see a bunch of letters mixed with numbers on a page, I want you to just completely cast those preconceived notions aside for a minute. Let's forget about textbooks and just start by playing a visual puzzle together. Okay, let's look at this beautifully balanced mobile hanging right here. At the very top, you'll see the total weight is 24. Now, because it's perfectly balanced, hanging totally level, that means the left side and the right side absolutely must each carry half of that total weight. So that's 12 on the left and 12 on the right. Simple enough. But we're given one really crucial piece of information here. A starfish equals 2. So looking at the left side, we've got 3 of those starfish and 2 blue fish. If every starfish is 2, well, those 3 starfish give us a total of 6. But remember, that whole left side needs to add up to 12, right? So what about those 2 blue fish? And for that matter, what about the gray submarine over on the right side hanging with just one single blue fish?
I'm going to pause for just a quick second here. Can you mentally calculate those missing weights? Let's figure it out. If that left side needs to be 12, and the starfish are taking up 6 of that, well, then those 2 blue fish just have to make up the remaining 6. Which means one single blue fish has to be 3. Okay, and over on the right side, we know it also has to equal 12. If the blue fish is 3, that leaves the submarine weighing exactly 9. What's absolutely wild here is that if you just followed along and solved that puzzle with me, you might not have even realized what you just did. You were performing complex, multi-step problem solving. You were literally doing algebra.
To really wrap our heads around how we just did that so intuitively, we need to look at the absolute foundational concept of algebra. And honestly, nothing illustrates that core concept better than a simple balance scale. Look at the scale on the left. We have a total of 4 at the top and 2 little characters, each carrying a weight of 2. 2 plus 2 equals 4. It's perfectly level. Then on the right, we've got a total of 7, perfectly balanced by a 4 and a 3. This perfectly level bar, it's the secret to literally everything we're talking about today. Both sides must carry the exact same weight to stay level. If one side is even a tiny bit heavier, the whole thing tips over. This physical, real-world reality of balance is the exact same logic that governs algebraic equations. So let's bump up the difficulty just a hair and see how this builds. Here we have another scale, and yep, it's perfectly balanced. But this time, we've got a mystery on our hands. On the left plate, there's this unknown sack, plus a 2-kilogram weight. On the right plate, there's a 10-kilogram box, plus another 2-kilogram weight. Your brain is probably already shouting the solution at you, right? You immediately want to figure out the exact weight of that mystery sack. But to do that systematically, we need to figure out how to isolate it while keeping our imaginary scale perfectly, flawlessly level. How do we get that sack entirely by itself without tipping the balance? Before we actually solve that sack problem, I want to pull back the curtain for a second on how we talk about these puzzles mathematically. On the left side here, we have the verbal description of one of those visual puzzles. 16 on one side, 4 and 2 flowers on the other. It's descriptive, sure, but man, it's a bit clunky to write out every single time. So, on the right side, we bridge the gap. We translate that concrete, wordy description into abstract letters and numbers. 16 equals 4 plus 2y. We simply replace the unknown flower with the letter y. We didn't change the underlying logic at all. We just changed the language. We formalized the puzzle. This right here is the exact moment where visual math transforms into written algebra. Which brings us nicely to our formal definition. An algebraic equation is a mathematical statement that indicates the equality of 2 algebraic expressions. Now, I want you to really lock onto that word equality for a second. In your mind, whenever you see that equals sign, I want you to picture the center pivot point of our physical balance scale. The equals sign is not some command telling you to compute the answer. Not at all. It is a firm statement of perfect balance. It's a guarantee that whatever sits on the left side weighs the exact same amount as whatever sits on the right side. And that leads us directly to this beautifully simple concept. LHS equals RHS. Left-hand side equals right-hand side. So the absolute crucial point to take away here is that finding a solution to an equation simply means we are hunting for the specific value of our unknown, whether that's our mystery sack, our starfish, or the letter Y, that makes the left-hand side perfectly, identically match the right-hand side. When LHS equals RHS, our scale is level, and our puzzle is officially solved. So how do we actually do this without just, taking wild guesses? Well, there's a highly effective, totally systematic method that empowers us to tackle any problem by treating it exactly like manipulating physical weights. Step 1. frame the equation. We just translate our real-world problem, or our visual scale, into math language. Step 2, and this is the magic step, perform the same operation on both sides. This is exactly how we manipulate the equation without breaking that delicate balance. Step 3, find the unknown. By carefully choosing our operations, we just chip away the extra weights until only the unknown is left standing. Let's see exactly what that looks like in practice. Let's put those steps into action right now. We've got a balance scale here. On the left, 2 unknown sacks. On the right, a 10-kilogram box, a 4-kilogram triangle, and one of those exact same unknown sacks. It begs a really brilliant question. Can you remove objects so that the sacks are only on one plate? Think about it like physical objects. If I literally reach out and take one mystery sack off the right plate, the scale's going to tip, right? The right side will instantly fly up because it's suddenly lighter. But if I use my other hand to simultaneously remove one identical mystery sack from the left plate, what happens? The balance is totally maintained. By performing the exact same operation, removing one single sack from both sides, we've isolated our unknowns onto just one side without ruining the equality. We're left with one sack on the left, perfectly balancing 14 kilograms on the right. Boom! Puzzle solved. This brings us to the absolute golden rules. You can think of these as the unbreakable laws of the algebraic universe. First up, equality is maintained when the same operation is performed on both sides of an equation. Add weight to the left, you gotta add the same to the right. Take half the weight off the right, take half off the left. Second, finding a solution actually requires finding the exact value that makes the LHS perfectly equal to the RHS. And finally, we deliberately use these mathematical operations to make the value of the unknown totally evident. We just peel away the extra numbers until the answer is staring us right in the face.
All right, we've talked theory, we've looked at the scales, and we've codified the rules. Now, let's have some fun and put this into practice. Are you guys ready to try a math magic trick? This is a fantastic hands-on application from the chapter to test out your newly acquired, highly systematic algebra skills. And the best part? It completely proves that what looks like mind reading is actually just the unbreakable rules of balance at work behind the scenes.
Okay, I'm gonna walk you through these exact steps, and I want you to actually do the math in your head right now as we go. Step 1, think of any number at all. Got it? Okay, keep it safe in your brain. Step 2, now multiply that number by 2. Step 3, add 10 to your new total. Step 4, take that whole number you have right now and divide it by 2. Step 5, now pay attention, this is the critical step. Subtract the original number you thought of right at the very beginning. Step 6, finally, add 3 to whatever you have left. Now look, I can't hear you, and I obviously have no idea what number you started with, but because of the rules of algebraic equations, because we performed symmetrical operations that neatly isolated and then totally eliminated your original unknown variable, I know with absolute mathematical certainty that the number currently in your head is 8. Crazy, right? Isn't it just fascinating how the unknown can mathematically vanish into thin air when you know how to balance the scales? Try mapping out that exact magic trick as an algebraic equation later on in your own time. See how the letters literally cancel each other out? It's awesome. Well, until next time, keep looking for the balance in everything, and keep on learning.